So what if your surface is parameterized as x and y, parameterized in two variables x and y? Can we get a general form for that? Can we like kind of work through the flux integral in this general case where z is a function of x and y, and we can parameterize the surface this way? Can we work through and get a general formula for this so that we can save kind of a lot of this heavy lifting in between if we know we're starting off with a surface that's of this form? Does that make sense? All right, so what do we need? We need Rx cross Ry, first of all. And so what do? We do IJK. I'm doing Rx cross Ry. So I need Rx in the second row and Ry in the third row. So Rx is 10GX. Thank you. There we go. This is better. And then, so that's Rx. And then Ry. 1GY. So this has nothing to do with the curl. I want the cross product. This thing. I want this thing right here. All right. Now we're on track. So cross product is going to be opposite GX. It's better than negative GY and 1, right? So what is the so looking at this, how is the surface oriented if this is our Rx cross Ry? Where z is a function of x and y, right? What's the orientation according to that cross product? How do you know that it's upward? Because z is positive. See that? See, because the z component of that, this is our n, right? This is basically our n vector. And because the non-normalized version, but because that is, these n vectors have a positive z component, that means that would imply upward orientation. Okay, and so then this thing equals F is that's F dot okay, so then this is dA, that is truly dx, dy, dx. Oh my gosh, what am I doing? P, Q, and R. See, I told you this is hard. Even your teacher can't do it. It's not true, I'm just rushing. Okay, so this is F dot the cross product. Okay, so here comes the general form then. So then it's going to be negative P gx minus Q gy plus R. And now this is going to be what? Over the projection of the surface in the xy plane, right? So this is going to be your limits of integration. Now we've got a double integral. The limits of integration are going to be the projection of your surface into the xy plane. Projection of S. I think we called that D or something. Yeah, we called that D. So here's a general form. So if you're doing a surface integral and you have this thing where you're parameterizing your surface in terms of xz, in terms of x and y, because z is a function of x and y, then you can just jump right to this for the flux. You get your P, Q, and R from your F, and then you got your partials of the function, of the surface, the partials for the surface, and then you can skip right to that. But this was for what kind of orientation? Upward orientation, right? Z positive, because of that positive 1 that we got right there, right? Okay, are you just clarifying, or did I make a mistake? Is it good? Okay, good. Does that make sense? So this is just kind of a shortcut for your flux integral whenever your surface is parameterized as x and y. Anybody have a question? Yes, please.
If the surface wasn't z equals x, y,
Mm-hmm.
it was like y is equal to x, z.
Yep.
Would your component with the constant in it, would it change based on
Right. So there, you could derive a formula very similar to this if y was a function of x and z, and then a different one if x was a function of y and z. So there's kind of 3 of these shortcuts. This is the one we see the most, so this is the one I derived. So it would take you 3 minutes to derive the others. So you're absolutely right. Yeah, so then if it was y as a function of x and z, then you'd have a plus q, and you'd have this something similar. Okay, exactly. Other questions? Okay, not enough time to do these exact examples. We'll do as best we can. Can I erase and go on? Okay, so here's the problem that we want. We want the part of the unit cubed below y plus c equals 1. F equals xy, y squared z with inward orientation. So now this is a closed surface. Like I said, I don't think you had anything like this on the homework. You had all just open surfaces. So the unit cube is in the first octant, has corner 0, 0, 0, and then kitty corner 1, 1, 1. And so then we want the part of that that's below y plus z equals 1. So the part of that, so y plus z equals 1, just as a line in the yz plane is this, but then that's a plane as you extend x, right? That's a plane like this. So we want the part of the unit cube below that, so like this ramp. Right, the solid ramp. Okay, so what does it mean to do the surface integral of this closed surface, this wedge, right? What would that mean to do that surface integral? So we want the flux across that whole shell thing. So what would it mean to calculate that? Yeah, so we're gonna have to add together. So basically we're looking at this right here. That whole thing is S. So the S has 1, 2, 3, 4, 5 sides, right? So we need to do the surface integral for each of those sides. And then when we add and get the flux for each of the sides with inward orientation, and then we add them all together to get the flux through the whole surface. Does that make sense? Okay, so let's label them. We'll do the bottom S1. We'll do the, I guess it could be you. Yeah, and then we'll do the that left side S2. And the front, S3, the back, S4, and then the slanted top we'll call S5. Back. All right, so here's the thing. There's that, I told you there was that alternate form, right? So F dot RU cross RV dA, but then I also said that there is F dot N ds. Okay, so when can you use this? This makes your life a whole lot easier. You can use this when you have a planar surface, like a rectangular. You're going to use rectangular coordinates, and you have a plane that's parallel to one of your coordinate planes. So you have rectangular coordinates, so not for polar. And a plane parallel to a coordinate plane. Because then you can just call n is just going to be a vector like 1, 0, 0, or 0, 1, 0, or 0, 0, negative 1, something really easy, and that makes your surface integral a lot faster. And then also, because it's a rectangular coordinates and you're parallel to the coordinate plane, ds does equal dA. This is the one case where ds does equal dA. So you can just do dx dy or dy dz, etc. Okay, so this saves you computing the cross product, and you can just jump right to f dot n and then use dA for ds. That works. If you have rectangular coordinates and you have a plane parallel to one of the coordinate planes. So you see that that's what we have in 4 of the cases here, right? So the back, the front, the bottom, and the left side all will fit this bill. Does that make sense? So let's do S1 first. What did I say S1? What's the bottom? So S1 is so that is basically we could write that as R is X and Y, and then what would it be? So we just basically have X, Y, and Z is what? 0, right? So that's how we could parameterize that. What is N? Okay, and we want, so inward orientation will be 0, 0, 1 or 0, 0, negative 1? Inward orientation. So it'd still be 1, right? Positive 1. So you had it right the first time. Okay, and so then we can do this, we can use this, right? So it'll be the double integral of f, which is, so xy y squared, and what's z? Z is 0. So there's our f dot n, 0, 0, 1. And then because we have this very specific criteria met, then we can say dx dy, dA. And then x goes from 0 to 1, and y goes from 0 to 1. And that equals 0. Did you follow that? Did you follow everything I did there for that? That was the bottom. Tell me, what did I do? Because the surface is, what surface is it? Yeah, so my surface is x, y, 0. So z is 0. So when I get to the, I'm going to use my parameterization, my surface, to rewrite f in terms of x and y. So z is 0 for that one. Are we good? S2 is which one now? Left side. So how do we parameterize it in terms of x and z? And it is x, 0, z, because y is always 0 on that left side. We can use, so we've met the criteria to use this, n equals. So inward orientation would be 0, 1, 0 for inward orientation. Double integral is, so we're going to have 0, right? Because f is y is 0, y is 0 again. Yes, sir.
Would it be 1 if we're talking about the left side for parameters or?
No, y is 0 here on the left side of this thing.
Oh, okay.
You see? Yeah. Okay, and then so we got y is 0, and z is just z. Dot. N is 0, 1, 0. dA, integral equals 0 again. It's going well so far. It's easy. S3 is the front. So, and then if we were to, it's fine. S3 is the front. Parameterizing the front in terms of what? Two variables?
Y and Z.
Y and Z. And that parameterization will be x equals 1, y, z. Again, we're using rectangular coordinates. We're parallel to a coordinate plane, so we can use this form and just write down what n is. N is inward orientation would be -1, 0, 0. Okay, ready to write the integral? Flux integral is xy is what? Y. Y squared is y squared. Z is z dot -1, 0, 0. Is it 0?
No.
Not 0 this time, right? This is actually going to be something. So we could do, we're going to project that into the YZ plane. We could do dz, dy, do type 1. Z goes from what to what? 0 to 1 minus y, right? And then z goes from 0 to 1. So that's going to be something. It's not it's something non-zero. Okay, S4. And I'm going to come up here and erase S1. So S4 is the back. Two variables we want for that are y and z again. Parameterization is 0, yz. Inward orientation means n is 1, 0, 0. Inward orientation on that back thing. So we get xy is 0, y squared z, and 1, what did I do? I'm back. 1, 0, 0. dy dz, that one equals, that one's 0, 2. You do the dot product, you get 0. So S4 is 0. So the last but not least is S5, which is the slanted plane. Let me stop and see if anyone has a question. Anyone have a question? See what we're doing. So we're kind of doing these individual surface integrals kind of rapid fire, and we're using this thing to our advantage. Now the slanted plane, we don't want to use this, okay? Because it's not parallel to a coordinate plane, so we're going to go back to our general form. But we had that special case. Remember that? Where y is a function, z is a function of x and y, right? So we can use that and save us calculating the cross product. So for S5, we're going to R is a function of x and y. And what is it? X, y, and 1 minus y, right? So that's like our G. We said this. Well, this is the parameterized version of that thing. And our F is then xy, y squared, and z is 1 minus y. So here's our P, Q, and R. And so then we just need, so we don't even need this, right? All we need is z equals 1 minus y, and then we're doing that partial with respect to x and that partial with respect to y. So we don't even need this. We're going to use that formula for what? Is it minus pgx minus qgy plus r? But we have to consider something here. What do we have to consider here? What was that for? Upward orientation. What do we have? We have downward because we're doing inward orientation on the solid means downward orientation on the top. So what would that mean for us then? Just take the opposite of all this. So we're going to do downward orientation would be plus, plus, and minus for downward orientation. So here we go. P is xy. Gx is partial of that with respect to x. 0 times 0. Plus q is y squared times gy is -1 minus r, which is 1 minus y. dy dx and this is the projection of this thing into the xy plane now. That's our limits for the double integral. 0 to 1, 0 to 1, right? That just projects as the unit square. So that's going to be non-zero. So this is the surface integral for the slanted top. And this is the surface integral for the front. Is that right? And then to save time, so we can at least get started on the next example. Yeah, there.
Isn't it, wouldn't it be z minus z at the end, not minus 1 minus y?
No, we've parameterized it in terms of x and y. So z is 1 minus y. Yeah. So you're right, it is z, but in terms of x and y, that's 1 minus y.
Mm-hmm.
Yep. Okay, and then you can confirm these added together then is -1. You get like -1/6 for one of them and -5/6 for the other. I think this is -5/6. And this is -1/6. And so then the whole flux, the inward flux on this whole thing ends up being -1. Questions on that example? So I've kind of introduced to you this shortcut whenever you have a surface that's you're going to do in rectangular coordinates parallel to a coordinate plane. You can use this, just go right to f dot n, and that saves a lot of time. And then whenever you have a z as a function of x and y, there was this thing that we derived today that makes it simpler. You can avoid the cross product and go right to that. And we switched the signs because we wanted downward orientation. Any questions on that one? All right, so let's just look at the next one. We won't be able to finish it. Can I erase what I have up there? So I want to do the flux through S is the closed surface. It's the part of the cone, our standard cone. And below z equals 4. So this surface, this is a closed surface, so this is z equals 4. It's the disk at z equals 4. And then this is z equals radical x squared plus y squared. So this S consists of an S1 and an S2, so we could say S1 is the cone, and S2 is the upper disk. And we're going to have to add the surface integrals together to get the total flux for the whole solid, for the whole surface, closed surface. All right, so for this one, how about the z equals 4? Do we want to use the f dot n shortcut for that, since it's parallel to the xy plane? Not rectangular coordinates. So we're gonna, since we're gonna use kind of polar coordinates for that, for both of them, we're gonna do, these both are gonna be done the long way, okay? So we're not gonna use the shortcut for this, and we're not gonna use z as a function of x and y for this, because it's gonna project into that cone's gonna project into the xy plane as a disk. So we're gonna go ahead and do cross product, do RU cross RV, which is gonna be what, RR cross R theta for both of them. So let's just write the parameterized surfaces. So for S1, let's just write what the surfaces are going to be. So R1 is going to be in terms of what? R and theta. So we're going to need to write this cone in terms of R and theta. So how are we going to do that? What's the x component going to be? Be R cos theta. Y component? R sine theta. And then what's the z is r, right? So yes, the height and the radius are the same. And you could do the math. You could do this equation on r cosine theta, r sine theta, and you'll get z equals r. Or you could just argue that the height is the same as the radius for that standard cone. All right, for S2, R2 is going to be r and theta again. All right, what's the x component going to be? R cosine theta, right? Because we want to need all the points all the way around and all the way from the center out to the edge. We need all those points filled in there. And then z is 4. Okay, so if we want outward orientation, that means when we do the cross product, we're going to look at the z coordinate, and we want it to be what for S2? Positive, right? And then when we do the cross product for this for S1, we want outward orientation, we want the z to be negative, because we want all the components of those vectors to be downward in order to get outward. So you're going to do the cross product, and then make sure that your z is negative on this S1, and then do the cross product and make sure your z is positive for S2. So we'll put it up there.